Okay, everyone, the live stream has started.
Great. So I think we can start. So a warm welcome to everyone. I'm Manish. I'm the executive head of Sparks. First of all, I would like to thank our speaker, Professor Patrick Dasgupta, respected principal sir, Dr. Jaswinder Singh, our department convener, Dr. Nimi Singh, all our respected professors, and all our guests for joining us today for the very first lecture of the Perennial webinar series, Quantum Magic and Miracles. So let me quickly brief you with the guidelines to follow throughout the webinar. Please keep your mics off throughout the webinar so you don't disrupt the flow. If you have any questions or queries, feel free to put them in the chat box. You will be called out by your name to ask your question in the interactive session, which will be held at the end of the lecture. That is when you can unmute yourself and ask your question. This lecture will be live streamed on YouTube. So if you want to invite any of your friends to attend this, you may provide them with the link in the chat box. All of these guidelines will be posted in the chat box as well. Now I would like to hand over the spotlight to Nima ma'am. Nima ma'am, you can start now.
Thank you, Manish. Respected principal, sir, our esteemed guest, Professor Dasgupta, Patrick Dasgupta, sir, my colleagues present today, and my dear friends. Very warm welcome to you all in the first lecture of the Perennial webinar series, which is hosted by Sparks, our physics society. And I'm really grateful to our teachers, especially Sushil, Savinder, Damo, and my students, Kabir, Manish, Garvit, Suhas, Pritpal, who have actually made a lot of efforts and have worked very hard in reviving this society after 2 years and initiate this lecture series. We are planning to hold, I think, one lecture a month. And in fact, I have actually no words to express my gratitude to Patrick sir for accepting our invitation and sharing his knowledge with our students, with us. And now, without wasting much time, may I invite our principal, sir, to please grace the occasion with his encouraging words.
Thank you, Dr.
Uh,
Nimi and
sir?
Manish, for having me here to welcome Professor Patrick Dasgupta. Uh, Professor Patrick Dasgupta is a very renowned professor of the University of Delhi, and I'm glad that he has accepted the invitation while being very busy, uh, you know, in the assignment that he's doing, I think, in United States. And the area which we are going to talk about is which he is going to deliver the lecture is quantum magic and mysteries, uh, which is uh, which is going to be interesting not only for the students of physics, but I think for the entire set of science students, because quantum physics or quantum chemistry are very important to understand, and there is a lot of interest, especially when we are talking about in terms of cross disciplinarity in the national education policy. So in that sense, this is a very welcome initiation by the Physics Society, Khalsa College, and I congratulate all the teachers and the students for organizing this. Professor Patrick Das Gupta is not new to Khalsa College. He has been spearheading us in a certain sense, mentoring our teachers and many of our students also in the University of Delhi. And we are glad that he accepted the invitation to be here today this morning in India. I do not know what is the time, uh, in his place of work where he's currently placed. But
It's slightly above 9 o'clock in the night.
oh, so sir, we are
That's
disturbing
okay.
your
That's no problem.
night sleep then.
No, it's okay. I sleep late anyway.
Thank you, thank you. So over to you, Dr. Nimi, and once again, I express my gratitude to Professor Patrick Das Gupta and the entire Physics Society for organizing this lecture.
Thank you very much, Honorable Principal Professor Singh, for your kind words. And it is great that you are present. I feel honored by this.
Thank you, sir. Thank you very much.
Thank you, sir. Thank you, Patrick, sir. And a special welcome to Rawat sir also, who has actually found out time in joining us. Thank you, sir. And thank you, Patrick, sir. So now, without
Most
wasting time,
welcome.
let us start with the lecture series. Over to you, Manish, please.
Before
Thank you, Professor Nimi Singh,
Sir,
for the kind welcome. And I also thank the Sparks Physics Society for inviting me. And it's great to see my old friend, Professor
and
Rawat.
your old students also. I think you remember me, right?
Of course. You, Anu, you were in
Yeah,
the same batch, right?
yes. No, no, she was senior to me.
Okay. Probably
And
um,
yeah,
uh, Harvinder was also senior to you?
yes, yes, 1 year senior to
Okay.
me.
Okay. Okay. Okay.
Yeah.
okay.
Okay, Manish, you
So
can start.
before starting on with the lecture, I would like to invite our president, Garvit Kumar Tehan, to speak a few words about our wonderful speaker. Garvit Bhaiya, over to you.
Good morning, ladies and gentlemen, and good evening to Professor Patrick. Uh, Most of us are familiar with classical physics, which explains the macroscopic aspects of nature. However, doing so at the microscopic level is inadequate. Quantum mechanics enters the scene at this point. Many renowned scientists created the groundwork for quantum mechanics, including Niels Bohr, Werner Heisenberg, and Erwin Schrodinger, to name a few. Where classical mechanics failed, quantum mechanics was able to successfully describe the intricacies of our cosmos at the microscopic scale. As our honorable principal sir has already mentioned, that this lecture will be interesting for all the students in the field of science, because quantum mechanics has a wide range of applications today in the fields of physics, chemistry, optics, computers, and medical research. With this remark, I welcome you all to Professor Patrick Dasgupta's webinar on quantum magic and miracles, organized by Sparks, the Physics Society of SGTB Khalsa College. Professor Patrick Dasgupta earned his doctorate from Mumbai's Tata Institute of Fundamental Research. In 1988, he became a postdoctoral fellow at the IUCAA in Pune. During 1989 and 1990, he worked as a senior research fellow at the University of Wales in Cardiff to learn about the gravitational wave data analysis techniques, and at the Observatoire de Paris in Meudon to experience gravitational radiation from the Hulse-Taylor binary pulsar. He joined the University of Delhi's Department of Physics and Astrophysics in 1993 and has been a full-time professor there since 2004. His current research interests include combination of the Hawking area theorem uh, from observed gravitational waves from binary black holes, proposing a unified model for gamma ray bursts and fast radio bursts, modeling dark energy, torsion, and Kern-Simon gravity using a dynamical four-form, and mechanisms to generate supermassive black holes from Bose-Einstein condensation of bosonic dark matter. I now invite Professor Patrick Dasgupta to begin with the session.
Thank you very much, Garvit. I take this also opportunity to thank the Sparks Physical Society, Garvit, Manish, and all others involved. And I thank Dr. Nimi Singh, Professor, Honorable Principal Professor Jaswin Singh, and the entire Khalsa College for giving me this opportunity to talk about one of the most fascinating subjects in the field of physics. I hope I am audible to everyone.
Yes, sir.
Very good. So the main reason I chose to talk about this field is right now where I am located, namely in the middle of the Silicon Valley. Everyone is talking about artificial intelligence, and one of the projected areas where the computer scientists are keeping their fingers crossed is the field of quantum artificial intelligence. When the quantum computation becomes a reality, the quantum artificial intelligence will also take off. And we are now living in very exciting uh, times where robotics, artificial intelligence is going to soon become everyday experience. And once the artificial intelligence embraces quantum physics, then there is absolutely no limit to the level of problem solving and the level to which progress can be attained. Right. But let's go from very basics. Entire world, of course, is quantum mechanical because everything is ultimately made of tiny quantum systems like uh, quarks, electrons, atoms, molecules, which are all governed by quantum mechanics. And we will soon see that as far as physicists know, that there is no limitation to the size as far as the applicability of quantum mechanics is concerned. Even 10 raised to power 8 atoms together have been seen to behave like a quantum mechanical system. I'll talk about it soon. But let's proceed a little bit historically. We know that as soon as photoelectric effects got described by the so-called E equal to h nu formula, and de Broglie proposed that any particle that has momentum mv also behaves like a wave with the de Broglie wavelength given by Planck's constant divided by the momentum. And thereafter, Schrodinger proposed his Schrodinger equation to describe the time evolution of the quantum system. And from the quantum physics itself, the uncertainty principle came in to show the limitation of classical physics. We know that the entire quantum physics revolutionized not only the world of physics, but also the world of philosophy, because of the fact that prior to quantum physics, randomness, probabilities, they were measures of our ignorance, but it is quantum mechanics which told everyone that the world intrinsically is probabilistic. So indeterminism no longer was just a matter of our ignorance about the world, but the world itself is now understood to be intrinsically probabilistic. And this can be very well described by the two-slit experiment. So imagine that you have an opaque screen with two slits, and you have a source which is emitting photons every 2 minutes, let's say. So that means uh, at a single instant of time, there's only one photon propagating, and therefore the photon either goes through slit 1 or slit 2, as classical physicists will uh, believe. But yet, after waiting for maybe 1 year, you will start seeing that the intensity of photons that is detected on a screen like a photographic plate or a scintillation detector, you will find that there is an interference pattern with a maximum at the center. There'll be a minimum, then local maximum, local minimum, etc., which tells us that even though one photon is being emitted every 2 minutes or so, the single photon is actually going through both the slits at the same time in order that you can get the interference fringes. So in other words, when you detect the photon on your photographic plate or your scintillation screen, you detect it as a single photon. You will never detect half a photon or 1/3 of a photon. You will detect a single photon. But when you are not detecting or observing the photon behaves like a wave. It goes through two slits at the same time. Remember, it is single photon itself behaves like a wave. So it is like the Hamletian dilemma, when to be a wave or when not to be a wave. So indeed, if you do the experiment first with one of the slits closed for the half of the time, and then open the slit and close the other slit, and then see whether there is interference, you don't see interference effect. In other words, you see interference effects only when both the slits are open. So it means that even though a photon every 2 minutes is being released from the source, when both slits are open, only then you see the interference pattern. The other thing which quantum mechanics did was to explain that why matter like us or the laptop that I am viewing or the table and the chair which you see all around, they are stable only because of quantum mechanics. If quantum mechanics was not there, then electron going around the positively charged nucleus would have spiraled in less than 10 to the power minus 8 seconds, and electron would have fallen on the proton, annihilated, giving rise to neutron and a neutrino, provided there was, of course, sufficient energy, because some of the mass of electron and proton is less than some of the neutron. But if you give enough energy to the electron and proton would have combined to give rise to neutron and neutrino, and neutron anyway is unstable. So in other words, it's only because quantum mechanics tells us that the electrons are not really going around the nucleus, they are not accelerating, and therefore you cannot use Maxwell's equation to say that they are radiating and therefore they must spiral in. Rather, there are no trajectories itself. No particles actually go along trajectories because trajectories violate uncertainty principle. Why so? Because if you have a trajectory, after all, what is a trajectory? Trajectory means that the position as a function of time is completely known. But if the position vector as a function of time is completely known, then even the momentum vector at any time can be found out, because the tangent to the trajectory, that means dr by dt, is the velocity, and mass times velocity is momentum. So if you knew the trajectory for all times, you also know the momentum for all times. But this is not possible because of Heisenberg's uncertainty principle. So what this argument shows is that no particle can actually have a trajectory, and therefore electron is really not going around the atom. So what exactly is the electron doing? We will come to that shortly. You might say that all these are all very, queer and strange. But the fact of the matter is, all predictions of quantum mechanics so far have been verified to 99.99% confidence level in all experiments done so far. So in other words, although quantum mechanics, we being viewing the world from the glasses of classical physics, therefore we find the workings of quantum physics very strange and queer. But the fact of the matter is, all predictions of this bizarre field of physics have been verified in experiments conducted so far. The other thing, of course, is that if you consider averages, on an average, if you do the averaging of quantum mechanical predictions, the Newtonian physics emerges. But there is a mystery in the averaging part. There is a mystery. If I get time, I'll talk about it. And that particular aspect of mystery has not yet been solved, even though 100 years have elapsed where great physicists like Einstein, Bohr, Schrodinger, Heisenberg, Dirac, Everett, Weinberg, whole lot of people have tried to solve this particular mystery, but so far we don't know what the solution is. The other thing I must point out, these are general features you might already know, but there is no harm in pointing out that quantum mechanics brought in the fact that the world, nature, actually is based on complex numbers. Before quantum mechanics, complex numbers were also used as tools in solving some differential equation or solving the solutions of a n degree polynomial. So complex variables were used as a tool, but classical physicists would say that we are only using complex variables as a technique to do contour integration, etc. But the real world is described by real numbers. But today we know that this is not true. Quantum mechanics cannot be done without complex numbers because the entire vector space, which is the state space for quantum mechanics, is a complex vector space. In other words, in position representation, the state describing a quantum system is described by a complex valued wave function. And Schrodinger equation itself has iota in it. So we know that the dynamical equation that tells us how the wave function evolves with time itself has the iota, which is square root of -1. In other words, our real nature is actually described in terms of complex numbers. So complex numbers are intrinsic to our nature. The other thing is, which is somewhat mysterious, I don't know whether anyone knows what the real reason is, at least I have not figured out why it should be, that wherever this square root of -1 iota appears, the Planck's constant also appears. That means in quantum mechanics, iota always comes along with the Planck's constant. As you know, it is Planck's constant which is the hallmark of quantum mechanics. It is the smallness of the Planck's constant which tells us that when systems are large, involving many atoms, you don't have to bother about quantum mechanics. Classical physics is adequate. Why is it so? Because look at the uncertainty principle. Uncertainty principle is delta x into delta p greater than or equal to h divided by 4 pi. You might say, then why is it that in the real classical world you have trajectories? When I throw a classical cricket ball, the cricket ball seems to take a trajectory. Where what happens to the uncertainty principle? The answer is that a cricket ball's mass is quite large. So your uncertainty principle, delta x into delta p, is delta x into mass into delta v, which is greater than or equal to h divided by 4 pi. So therefore, delta x into delta v is greater than or equal to h divided by 4 pi m, where m is the mass of the particle on which you are applying uncertainty principle. If h divided by 4 pi m is very, very tiny, then delta x into delta v can be as small as you wish. And therefore, you get back your trajectory picture for objects like a cricket ball or even for a dust particle. Right. So, the fact that even large-scale objects do show quantum behavior, that is what gives rise to this magical and miraculous event. One is the superfluid. We'll talk about it more, but I'm just giving it as an appetizer that when you liquefy helium, then helium shows very crazy behavior. Like, for example, if you lower an empty test tube in a beaker full of liquid helium and wait for some time, you will find that your test tube is now filled with liquid helium. Or if you take a test tube with huge amount of liquid helium in it and lower it in a beaker, after some time you will see that level of the liquid helium in the test tube has decreased and beaker is now full of helium. The whole thing will stop when the level in the test tube and the level in the beaker becomes equal. So the question is, why do this miraculous thing occur? Again, it's due to quantum mechanics. We'll talk about it soon as I proceed. Similarly, there is something called Josephson effect. If you take two superconducting material and put a very thin slice of insulator in between, and don't apply any battery or a voltage source, just connect them, you'll find current flowing. Again, this is magical, right? You don't expect that two superconductor with a thin sandwich of insulator, if you just connect, current keeps flowing. I mean, such a thing is not normally happens in your electricity experiments. So these are some of the magical and miraculous phenomena that is exhibited because of the fact that all these large systems are described by a macroscopic wave function. Right. So, of course, I will only be brief in remarking the history of quantum mechanics. Quantum mechanics arose because classical physics could not explain the black body spectrum, because the classical physics with the equipartition theorem, which said that with every degree of freedom, there is an energy of about half kT, and therefore for a black body, because there are infinite number of wavelengths being emitted in a black body spectrum, for every wavelength mode, you have to put a kT factor, then the intensity would keep on going higher and higher as you go for higher frequency. It's called the ultraviolet catastrophe, but that's not what we observe. The experimental black body spectrum is it goes up, has a maxima, and then again comes down. And the exact mathematical formula that explains this observed black body curve is given by the Plancks formula. And as you can see, Plancks formula explicitly has the Planck's constant h in it. Okay, and temperature, of course, is there, and Boltzmann constant k is also there. But Planck could theoretically derive this formula to explain the observed Planck spectrum by introducing completely a new idea. He said that at any given frequency, the number of energy bundle is finite, and each energy bundle is having an energy which is Planck's constant h times the frequency. So in other words, he was saying that given any energy, the number of bundles is not infinite, but number of bundles is, given the energy, divide by h nu, you will get the number of bundles having the frequency mu. Although he did not say that the entire electromagnetic energy comes in the form of bundle, but he used the same mathematics, but which Einstein, to explain the photoelectric effect, in which even very weak intensity but high frequency UV rays, when they fall on metals, they eject electrons out. And this Einstein explained by saying that the Planck's formula must be used even though the UV beam is weak, but it is comprised of discrete quanta, each quanta having energy h nu, and it is this each quanta of energy is knocking off electron. And because UV has a higher frequency, h nu is higher, and therefore it is able to knock off one electron. You can't do that even if you shine a high intensity infrared source, because infrared wavelength is long, above 800 nanometer, and therefore frequency is small, and therefore each of the infrared photon, they don't have energy to eject out the electron from a metal, because it doesn't have the required energy to overcome the work function. Then came the other challenge that when you heat up gases like sodium or hydrogen, when you heat them up to more than 10,000 degree Kelvin, then they start radiating. And when you take the radiation from such hot gas of sodium, hydrogen, calcium, etc., and pass them through a dispersive medium like a prism or a diffraction grating, what you see are discrete lines of emission. Unlike what you see for the radiation coming from the sun. If you take sun and pass the solar radiation through a prism or diffraction grating, you will see continuous band of radiation. But when you do it for sodium, hydrogen, calcium, etc., for that matter, any element, you only see discrete emission lines for different wavelengths. And this was explained. There's another slide for different elements and their uh, atomic spectra. And you can see that no matter which element you take, whether you take copper or mercury, all show discrete spectra. And this could not be explained by classical electromagnetic theory, because in classical electromagnetic theory, atom which contains a positively charged nucleus and a negatively charged electron as it goes around in the classical viewpoint, it goes around in a circle, then it has centripetal acceleration. Because of the acceleration, it will radiate according to Maxwell, and therefore, as it loses energy through emitting radiation, it will spiral in and fall on the nucleus. And then all material will be unstable. But the fact that you're listening to me, I am speaking, so that means we are all stable. So therefore, there is something wrong in this picture. And initially, it was Niels Bohr who gave an ad hoc model saying that when an electron is going around the nucleus, it can only be in discrete velocity levels satisfying mass of the electrons times speed of the electrons times radius of the orbit is some number times h divided by 2 pi. This is called the Bohrs model, and Bohr is an elementary thing. I'm sure you have all done it. With this formula, mvr equal to nh divided by 2 pi, you can get the hydrogen energy levels, which is minus 13.6 electron volt divided by n square. Okay, and it agreed with the spectral lines coming from hot hydrogen gas, but clearly it was a very ad hoc rule, and de Broglie, he wanted to give a more realistic interpretation to this ad hoc rule, and he of course was inspired by something else, namely if electromagnetic radiation can behave like particles like photons, why not particles behave like wave? And by using his special relativity, he sort of proposed that any particle that has a momentum mv is associated with a matter wavelength h divided by mv. And he could explain the ad hoc rule of Bohr by saying that if every particle is like a wave, then Bohr's rule just says that the orbit circumference, the length is such that you could have a standing wave. In other words, lambda equal to hmv clearly says that if you have mvr equal to nh divided by 2 pi, then the wave can form a standing wave. For all other radii, you don't have a proper standing wave, and therefore they are unstable. But the problem is that, again, it was a very ad hoc kind of model as to why should standing wave be more special than other kind of waves. But nevertheless, we know that the de Broglie wavelength idea has been shown to be correct for even large molecules, like for example the fullerene molecules, the so-called C60. That also shows if you pass it through a two-slit problem, you indeed see an interference pattern. And I will soon show a slide where 10⁶ atoms in Bose-Einstein condensate state, they also show such interference fringes when you pass them through two slits. So, to summarize, the matter wave duality proposed by de Broglie, along with the E equal h nu and lambda equal h by mv, they explain many things, including the photoelectric effect, the discrete spectra of atoms, as well as electrons when they are passed through two slits, they show interference pattern. Okay, and in particular, the original thing that I said about having an opaque screen with two slits and a source where photon or an electron is being emitted every 2 minutes, and after you wait for a long time, you see an interference pattern, has also been done. And there are YouTube videos where you can see how with time, slowly the interference pattern builds up. That is, initially, either a photon or an electron is being emitted every 2 minutes and they are passing through two slits. Initially, whenever an electron or a photon goes to both slits and hits the detector, you see one bright spot, another bright spot. That is, when you're detecting it as a particle. But wait for a long time. As you wait for a long time, soon you start seeing the dark fringe, bright fringe, and so on. And this is possible only when both the slits are open. So at the detection level, you're detecting it as a particle, but when it's transiting via the two slits, they behave like waves and interfere. So I will just tell you a little bit about the main problem regarding quantum mechanics that no one has yet given a satisfactory answer. It is this, is the collapse of the wave function. So we know that particle, when it goes through a larger slit, it is described by a broad wave function. But as I said, that when you detect it, so if you have a detector A and detector B, so when the electron or an atom passes through a slit, the wave function is quite broad, as broad at least as the slit to begin with. And you keep a detector, the detector can be very narrow. When the detector detects it, supposing the detector detects this broad wave, suddenly get localized here, you detect it as a localized particle. Or you need not detect it here. If there are two detectors, sometimes detector B will detect, sometimes detector A will detect. And which detector will detect, no one can tell you. That is where the probabilistic nature comes in. That is, a broad wave function, when you try to localize by trying to detect where the particle is, where you see is probabilistic. If A detects it, that time the broad wave function collapses to a narrow wave function. While if B detects it, then the wave function, the broad wave function will collapse here and the particle will be having a localized wave function here. Who will detect it? No one can predict. You can only predict with what probability you will see here or you will see here. And till now, no one knows why the collapse with some probability occurs. I'll tell you more as to why this can't be simply a matter of rule, saying that is the rule. I'll tell you why in a short while. But before I go into describing that why is it that whenever you measure the random collapse is a big problem for the entire quantum formalism, let me tell you also something about a philosophical mystery about quantum mechanics. It is this, that we know that entire world is quantum mechanical because the entire world is made out of atoms, molecules, which we know are governed by quantum mechanics. So John Wheeler, one of the greatest general relativists, he gave this insight. He said that, look, the universe began from some compact region. Classically, it's a singularity, but we know that if there is a proper quantum gravity theory, there'll be not a singularity, but there is some quantum fuzz. But universe began from a very compact and high temperature state. It was made out of electrons, quarks, neutrinos. As the universe expanded, it cooled down and neutral atoms were formed. Then atoms gathered gravitationally to give rise to galaxies, stars, planets. And in planets, finally, at least there was one Earth-like planet where living organisms arose. And finally, through Darwinian evolution, you had intelligent uh, uh, species like human beings, and human beings themselves are made out of atoms, molecules, which are quantum mechanical. And it is this atoms, molecules, they are now trying to understand the entire laws behind the evolution of the universe. So atoms, molecules, which are themselves quantum mechanical, are trying to figure out what are the laws that govern atoms, molecules. So therefore, it's a very philosophical puzzle that atoms, molecules, which finally have come into a complex system and given rise to life, consciousness, etc., they are trying to understand, they are meaning we are trying to understand the laws that govern the behavior of atoms and molecules, although we ourselves are made out of atoms and molecules. It's a philosophical viewpoint. Now, you might say that, well, wave function, after all, it is the wave function which evolves with time as given by the Schrodinger equation, but is there a physical significance of the wave function? The answer is yes, there is a physical significance. That is, if you have a wave function that you are looking from position representation, then in the position representation, wave function will be a function of position and time. So if you have a psi of r comma t, or in the one dimension psi of x comma t, then interpretation is that if the particle is described by a wave function psi, then mod psi square gives you the probability density of finding the particle between x and x plus dx. In other words, that if you do an experiment to find out where the particle is, then the probability that you will find the particle between x and x plus dx is mod psi square times dx. So in other words, you will never be able to predict where the particle will be found, but you'll be able to predict what the probability is to find where the particle will be. But when you find the particle here, let's say, the particle's wave function collapses to a very narrow wave packet here. And this collapse process is not understood even now. Okay, I've already explained this, so let me not go further. But one of the most important equation in quantum mechanics is the Schrodinger equation, which says that iota times h divided by 2 pi. H divided by 2 pi is the so-called reduced Planck's constant h bar. I into h bar into del by del t of the state of the quantum system is equal to one operator called Hamiltonian operator acting on the state vector of the system. This is called the Schrodinger equation. It tells you that it is a first order differential equation because there is only one partial derivative, and this tells me that if I know the wave function at time now, for example, then by solving this differential equation, I can find out the wave function at any later time, provided I know what is the Hamiltonian operator. This Hamiltonian operator physically is a Hermitian operator corresponding to the energy of the system. Okay, and as you can see, that iota appears in conjunction with the Planck's constant. This you will always find in quantum mechanics, that whenever iota comes, iota will always appear with the Planck's constant. I don't know whether anyone else has pointed out this feature, but I'm personally very mystified by this uh, uh, occurrence that I and H, I will occur only when H occurs, not separate. Right. Now, let me talk about the central problem of quantum mechanics, namely collapse. So, if you have a broad wave packet, so if the particle is not localized to begin with, let's say a particle passes through a very wide slit, then the wave function is quite wide. But we know that quantum mechanics, the wave function is a part of the linear vector space, and therefore in vector space you can always add vectors, and therefore you can construct this wide wave function by adding up many narrow wave functions. Is a vector space, so I can add all these and I can finally make up a bigger wave function. But when you measure, let's say you measure with some apparatus, you try to find out where the particle is, then bang, you will find the particle somewhere, and therefore its wave function is now very localized, very narrow. But where the particle will be found, whether it will be found here, whether it will be found here, whether it will be found here, you don't know. You only can find out the probability of finding where the particle will appear. But that is the whole problem. After all, if everything is evolving according to Schrodinger equation, there is no probability here. Schrodinger equation is a deterministic equation. And this Hamiltonian operator, when you are measuring, measurement is only an interaction between the quantum system and the measuring device. And the interaction will be governed by an energy operator, Hamiltonian operator. So you should be able to just solve the equation deterministically, and there are no probabilities. But fact of the matter is that whenever you measure, you do end up with probability. This is the central mystery of quantum mechanics, which no one has solved. It's not that people have not given good ideas. There are many good ideas, including the many world interpretation of Everett, which is the most popular interpretation. But there are many ideas. Penrose's idea of collapse being triggered by gravitational wave or graviton, or the Italian Ghirardi et al.'s group that there is a spontaneous interaction which is injecting a spontaneous randomness into the system. There are many models, but none of the models are free from certain problems. Right. We also know that uncertainty principle is fundamental to quantum mechanics. Although it is not part of the quantum postulate, but uncertainty principle can be derived from quantum postulate. But physically, uncertainty principle arises because everything, including a probe, that is, if you want to measure the position of a particle using a photon, because a particle is also like a wave, and the probe, like a photon, is also like a wave. So therefore, when you try to observe the photon after it collides with the electron or any particle, the photon's observation will be limited by the so-called diffraction limitation of a microscope. And when the photon interacts with the electron, it will give an uncontrollable momentum to the electron. So therefore, if you want to have a good resolution, the wavelength of the photon must be small. But if the wavelength of the photon is small, its frequency is high, and therefore it impart a greater momentum. So therefore, uncertainty of the electron's momentum will be high. So it is the wave-particle duality which is the physical cause of the Heisenberg uncertainty principle. And there's also another uncertainty, namely the delta E, delta T, the energy time uncertainty relation. Its status is somewhat different. Its status comes from the interaction of a system with another system. So truly speaking, the interpretation of delta E into delta T being greater than h divided by 4 pi is somewhat different. I will talk about it later on, but let me, because I'm running out of time, let me go ahead further. So one of the thing which uncertainty principle does is it protects quantum mechanics from various uh, paradoxes. For example, we know that virtual particles are created. So an electron and a proton, when they are interacting, they interact by exchanging virtual photons. The question is, how are the virtual particle being created? And there the uncertainty principle, which explains this delta E into delta T greater than h by 4 pi, it says that, well, when a virtual particle is created, yes, energy conservation is violated, but that energy conservation is violated by delta E time, and it violated only for a short time delta T. So that's how we explain creation of virtual particles. Similarly, by the way, this virtual particles being created spontaneously can also explain the so-called Hawking temperature of a black hole. As you know, black holes, classical black holes have an event horizon. Anything within the event horizon cannot escape out. But when a virtual pair is created near the event horizon, one of the particle can get into the event horizon and is completely lost to the black hole. The other particle can escape, and such particle which is escaping appears as a Hawking radiation. So Hawking radiation, which tells us that black holes truly are not black, is really a quantum phenomena. The other paradox that can be explained through uncertainty principle, we know that although in classical physics, if you have a tall hill and if some object's energy is not enough to reach the gravitational potential energy of the height of the hill, then you cannot make the object go past the hill to the other side. But quantum mechanics allows it, because in quantum mechanics, even if you have a potential barrier and you have a particle whose energy is less than the height of the barrier, then there is a probability that you will find the particle on the other side of the potential barrier. In fact, this is what was used by George Gamow to explain the alpha particle decay, because after all, if you have an unstable nucleus, then nuclear energy is very attractive, but there is an electrostatic barrier and the particles inside the barrier cannot classically go out of the electrostatic barrier. Like an alpha particle which is positively charged, the whole nucleus is also positively charged. But George Gamow invoked the tunneling principle, that although the alpha particle's energy is lower than the barrier, but since the barrier height is finite, it can tunnel out. And what is the basic simple physics to explain why tunneling is possible? Again, is the wave particle duality. The alpha particle is strictly speaking not a particle, but also is a wave. So if the wavelength is comparable to the barrier width, then the wave doesn't see the barrier. It encompasses and goes out of the barrier. This is a simple way of explaining tunneling, but you have to really use the Schrodinger equation to explain quantitatively how the tunneling occurs. And uncertainty principle can be invoked to solve paradoxes associated with tunneling, because you can ask that if the particle's energy is lower, let's say the particle's energy is this level, this is the energy level, while the barrier height is so high, when the particle is tunneling, that means when the particle is here, what is its kinetic energy? Where the potential energy, if it is here, the potential energy is this much, but its energy is this much. So kinetic energy has to be negative, but kinetic energy cannot be negative because kinetic energy is always p square by 2m. It's always positive. So if you detect the particle when it is tunneling, if the particle is here and you detect it here, then you know its potential energy is very high, but its original energy is only this much. So what happens to the kinetic energy? So how do you resolve this paradox? You say, well, uncertainty principle says that if you want to detect the particle here very accurately, then the uncertainty in the position must be less than this width. But if the uncertainty is less, then uncertainty in the momentum must be very large. And that tells you that the kinetic energy delta p square by 2m is so uncertain that it cannot be negative. So uncertainty principle helps you to resolve paradoxes associated with such object. Now, you might think that all this quantum tunneling are only theoretical object, but no, today you have this scanning tunneling microscope. The scanning tunneling microscope, through which you can see the electronic clouds around atoms, is actually based on this tunneling phenomena. So you have a tip, very sharp tip, and the tip goes above your crystal, and because there's a gap between the tip and the electrons, there's a tunneling, and the tunneling current tells you what is the density of the electrons. So indeed, your scanning tunneling experiment is based scanning the so-called scanning tunneling microscope is based on the tunneling quantum tunneling event. Now let me talk about the macroscopic quantum mechanics. So we all know about helium. Helium has 2 protons and 2 neutrons in the nucleus, and 2 electrons forming the so-called wave function, or the electron cloud around. Remember, there are no trajectories, there are only wave functions. So helium having 2 protons, 2 neutrons, and 2 electrons is a boson. And for a long time, helium could not be cooled, but finally, Kamerlingh Onnes, he managed to get the temperature down to 4 degree Kelvin, and helium became liquid. But then it was found that if you decrease the liquid helium to a temperature below 2.17 degree Kelvin, the liquid helium exhibited funny behavior. What is that? So supposing you have a flask of liquid helium and you decrease the temperature below 2.17 degree Kelvin, then you will suddenly see spontaneous fountain of liquid helium. Will just fountain out. And furthermore, it turned out that when you cool the liquid helium below 2.17 degree Kelvin, the liquid cannot be rotated. It resists rotation. If you try to rotate, then the entire liquid breaks up into vortices. The black dots are vortices which have the rotation, but the vortices where it is rotating, it's not anymore superfluid helium, but the bright part which are not rotating, they are superfluid helium. Okay, so the superfluid, it doesn't rotate, it resists rotation. Wherever there is rotation, after all, if you physically rotate it, angular momentum has to go somewhere, and the angular momentum is carried by all these vortices. Vortices themselves have the rotation, but at the core of the vortices, you have normal liquid helium, not superfluid. And these can be explained, again, all by quantum mechanics. So this is the other thing I was talking about, that if you lower an empty test tube in a beaker full of liquid helium, after some time you'll find that your test tube is no longer empty. How do we explain this? One way you can explain is that if this superfluid helium is described by a wave function, then the test tube is like a gravitational barrier. There's a gravitational potential at the tip of the barrier. So, but the liquid just tunnels out, the wave function tunnels out, climbs, and goes into this. So immediately you can see that this phenomena can be explained using quantum tunneling, and truly speaking, superfluid helium should be explained in terms of macroscopic wave functions. And that is what is done normally. It turns out Bohrs and Einstein, they had predicted the so-called Bohrs-Einstein condensation in their work in the early 1920s. The idea is very simple. Normally, when we learn statistical mechanics, we talk about classical gas, kinetic theory of gas, where gas particles are randomly moving, and the random kinetic energy is what we interpret as temperature and so on. But Now with quantum mechanics, we know that these are not really particles, they are associated with wave function. So what you do is you cool the gas. If you cool the gas, the random velocities decrease and therefore the de Broglie wavelength increases. If you go down in temperature, then eventually it will happen that the de Broglie wavelength will be so large that will be larger than the typical separation between the atoms. When this happens, when the de Broglie wavelength becomes much larger than the separation of atoms, no longer you can think of them as collection of particles. Now the entire thing is like a macroscopic wave function. In particular, in the theoretical limit of temperature equal to 0, you have all bosonic atoms in one single energy level, and all are described by a single wave function. That is the ideal Bose-Einstein condensate. But of course, today we know that T equal to 0 cannot be achieved in finite steps. But in other words, Bose-Einstein condensation tells us that when you cool systems to a temperature so low that the de Broglie wavelength becomes larger than the separation of particles, you can attain macroscopic wave functions, and your liquid helium can be thought of as, the so-called superfluid helium can be thought of as a large fraction of helium atoms have gone into a Bose-Einstein condensate phase. Not all, of course, because when you decrease the helium liquid to a temperature below 2.17 degree Kelvin, not all particles have de Broglie wavelength which is larger than the separation. Those which have formed Bose-Einstein condensate, and they are described by a single macroscopic wave function, and the tunneling can explain why you have this magical feature of superfluid phenomena. So unlike fermions like electrons, quarks, bosons, when you cool, they all come to a single state. And of course, you can't go to T equal to 0. At T equal to 0, they'll be in a single state. But when you come to a very low temperature, most of the bosonic particles will be in the single state. This is different from fermions. Fermions, as you know, no two identical fermions can be in the same state because of the Pauli exclusion principle. And fermions, of course, they have their own peculiar behavior. All semiconductor device, all electronics, entire material science is based on the Fermi statistics exhibited by electrons and the holes. Right. So this is in early 90s when first Bose-Einstein condensation in the laboratory was exhibited. So here is a example. You're plotting the distribution of particles, a Bose-Einstein bosonic system of particles, identical bosons, and at temperature 200 nanokelvin, when you measure the velocities, as you can see, you have a wide spread in the velocities. Even at 100 nanokelvin, although there is a spike, but there is still a wider base. But when you go very close to few point decimal nanokelvin, you find a large peak. That means all the identical bosonic atoms have gone almost to a single state. So this Bose-Einstein condensation, actual Bose-Einstein condensation with atoms was attained in early 1990s. And Bose-Einstein condensation not only explains superfluid, it also can be used to explain superconductivity. As you know, that there are substances, what they exhibit is when you measure the resistance against the temperature, then as you lower the temperature, there's a critical temperature below which the entire resistance goes to zero. So, for example, uh, uh, mercury, if you decrease the temperature below a particular critical temperature, mercury becomes a superconductor. Resistance goes down. You have a solid mercury for which resistance is zero. The other feature is that superconductors are completely diamagnetic. That is, if you take a solid mercury above critical temperature and place it in magnetic field, the magnetic field lines will be going through the solid mercury. But if you decrease it below the critical temperature, the mercury will expel all the magnetic field. Inside, the magnetic field will be zero. So it has become completely diamagnetic. The other phenomena that a superconductor shows is that if you take a loop of superconducting material, if you have a wire loop, then uh, it can carry current, but it will carry current in such a way that the flux which it traps is integral multiple of a particular value, which is called the um, basic magnetic flux, which is about h bar divided by twice electronic charge. So therefore, the magnetic flux quantization is another hallmark of superconducting loops. And all these can be explained purely from the fact that what happens is in a superconductor, when you cool the temperature, their pair of electrons spin up and spin down, they form a bound state. Although individually electrons are fermions, but when two electrons spin up, spin down, they form a bound state, the so-called Cooper pair. They are bosonic, and the bosons, when they undergo Bose-Einstein condensation, now there is a macroscopic wave function, and it is this macroscopic wave function that is responsible for all the bizarre and mysterious properties of the superconductors, like throwing away the magnetic field or the resistance coming to zero, or the magnetic field being thrown away, is what you're shown normally, that if you take a magnet, a bar magnet, north south pole, and you take a high temperature superconductor, and when it was not superconducting, the bar magnet was resting on it, but you pour liquid nitrogen so that this high temperature superconductor becomes material becomes superconductor. Immediately the magnet starts floating because the superconductor is diamagnetic. You might ask that, well, two electrons, how can they form a bound state? After all, electrons, they have like charges, they should repel electrostatically. The answer to that is shown in this picture. What happens is that in a superconductor, you have the so-called lattice, crystal lattice, where at the lattice side you have the positively charged ion, and electrons are hovering around in the cloud. When you have cooled down, what happens is if you have a electron moving, then when this electron is moving like this, positively charged ions get attracted, they come together. So here suddenly the density of positive charge increases because all the ions are trying to be closer to this electron. So because of the excess positive charge, another electron far away, it feels the attraction. So there is an effective attraction between the two electrons. It is effective because it is not the charge of this electron which attracts this electron, but because this electron itself has attracted many positive ions close by, here the positive charge density has increased compared to this side, so this electron gets attracted. And therefore, it is this weak attractive force which causes the Cooper pair to form. And it can happen only at low temperature. Okay. And the other mysterious effect, which I have already described, so-called Josephson effect, where you take two superconductors and you separate them by a thin film of insulator, and if you connect it, there is a current, automatic current. You can ask, why is there an automatic current? The reason is this part of the superconductor is described by one wave function, this part by another wave function. But because there's a gradient in the wave function, you will soon learn in quantum mechanics that there is a probability current density which is related to psi star grad psi minus psi grad psi star. So whenever there is a gradient in the wave function, there is a probability current. So therefore, there's a probability current for the Cooper pairs, and the Cooper pairs, they go through. What maintains the gradient is the insulator. If there was no insulator, then there wouldn't have been a gradient. But because of the insulator, the wave function here and the wave function here are different. And because of the gradient side not being zero, there is a probability current which goes through, and it is that which causes the electric current to flow. So these are the bizarre properties that result from the macroscopic quantum phenomena. So what we have seen regarding Bose-Einstein condensation is that below a particular temperature, the wave function associated with particles, they become so large, they are large compared to the particle separation, and they become like a gigantic quantum mechanical system. By the way, nowadays, people have started creating Bose-Einstein condensate out of 10⁸ bosonic atoms, like either rubidium atoms or cesium atom. And this is an actual picture of a Bose-Einstein condensate passing through two slits and showing the interference pattern with fringes. And recently, just few days back, there was another experiment that was reported in the Nature magazine. Many authors, but the lead author is Vishwarup Mukherjee, where what they did was they took 1 million identical bosonic atoms and set them into rotation. So when the temperature was low, the atoms were rotating, and they were in the form of a pillar. So the atoms in the pillar, they are all rotating about this axis. But when they cooled down further and it became a Bose-Einstein condensate, all kinds of bizarre phenomena started happening. This rotation started becoming like a wave, as though there was a wave function, there was a wavelength in this direction. Then they started breaking up into pockets, and each of them, so they formed a crystal-like structure where here you have individual Bose-Einstein condensates, and if you go in between, there are normal, not Bose-Einstein condensate, but normal atoms which are counter-rotating. And this is one of the latest experimental findings reported with Bose-Einstein condensate with rotation. And what the authors claim is as though there are these quantum tornadoes, just like there are these hurricanes and tornadoes, that you do something here, butterfly effect. Even a butterfly fluttering about somewhere can lead to a tornado somewhere else. Similarly, in quantum systems, a tiny disturbance somewhere can give rise to all kind of bizarre phenomena. By the way, I don't want to talk about my work related to Bose-Einstein condensation and formation of supermassive black hole. Those who wish to do can, here is the reference. But I would rather interact with the students. I want to discuss with them than report. One of the biggest thing about quantum mechanics is entangled state. That is, the degrees of freedom, one degree of freedom get entangled with other degree of freedom, and that gives rise to all kinds of bizarre phenomena. The entangled state was first talked about by Schrodinger and in its Schrodinger's cat paradox, that is more than anything evident what he was meaning by entanglement. So the so-called Schrodinger cat paradox goes like this. Supposing you take a radioactive nuclei like cobalt 60 and you put it in a box, and there is a GM counter which is connected to the amplifier, and any decay, it'll go through the GM counter and there'll be a click, and the click will be amplified, and it'll run a tape loudspeaker relaying this talk. And the idea is if there is a click, then the current gets amplified and it relays this talk, and the talk is heard by the cat, and cat dies out of boredom due to the talk. If there is no decay, then there is no amplification, there is no talk heard by the cat, and the cat lives. And what is the entanglement Schrodinger talked about? That cobalt 60 being a quantum mechanical system, it's in a superposed state. Either the state is that of a cobalt 60 nucleus, that means it has not decayed, or the cobalt 60 nucleus has decayed. And in general, every instant you have a superposed state. Once you put them in conjunction to a macroscopic device like a Geiger-Moller counter, then the Schrodinger equation, what it will tell you is that it will bring a correlation. When you solve the Schrodinger equation with cobalt 60 with a detector, the solution will be, final solution will be, if there's a decay, there's a click in the GM counter, and because of that, there's a current flows and talk is relayed, and because the talk is relayed, cat is dead. But there's also the other no decay channel, no decay, no click, no talk, no cat. This is an entangled state, as you can see, because cat dead and cat alive are entangled states with decay and no decay. Okay. So Schrodinger equation, when you evolve, you will get this. Schrodinger asked this question, that the Schrodinger equation gives this, but when I open the box, I don't see this entangled state. I see either the cat is dead or the cat is alive. So the collapse, who caused the collapse? And that is the fundamental problem of quantum mechanics that has not been solved. Because Schrodinger equation, when you evolve, you get this superposition of these correlated state, which is the so-called entangled state. But when you actually open the box, you will only see either the cat to be dead or alive. So when did it collapse to either this branch or that branch? In the many-world theory, there is no collapse. Rather, in the many-world theory, every time you measure, the entire universe splits up into branches. But the whole problem is the many-world theory cannot explain where the probabilities come from. That is still a problem. Well, there are many things I wanted to talk about, like how lasers are essentially quantum device and so on, and how they are being used in LIGO detector and all that. There are many mysteries in quantum mechanics, but I mean, if I talk too much, it'll only be a set of information, and it'll not be retained by many minds. So it is more important that I stop and you ask me questions. That is more important.
Okay, great.
Because I noticed that I have gone on for a long time. It's better that we interact and we have question answer sessions.
Yes, sir, we have quite a few questions.
Yeah, you can read them out.
So I should read them out, or shall I ask the students to unmute and ask their questions?
Yeah, that is better. That is in fact time saving.
Okay. So Soumyadeep Sarkar, you had your questions. Would you like to unmute and ask, or should I take your questions out?
Yes, yes. How was Heisenberg's uncertainty principle? How did he came up with this idea of uncertainty principle, and how was it experimentally proven at first? I'm asking.
Yeah, so Heisenberg got to this idea by two means. As you know, when he was trying to described the atomic spectra, what he was doing is he was writing matrix representation for position operator, momentum operator, and so on. He had developed something called matrix mechanics, where every physical variable was represented by a matrix. But then Heisenberg, being a genius, he realized that position matrix and momentum matrix, they don't commute. That means x multiplied by p is not equal to p multiplied by x. And from that, he realized that you can't simultaneously diagonalize the two matrices. You will soon prove a theorem that two matrices can be diagonalized simultaneously using the same similarity transformation only if the two matrices are commuting, only when they commute with each other. If they don't commute, then they cannot be diagonalized. From that, Heisenberg guessed that position and momentum, they cannot be measured simultaneously at the same time. But that was too abstract. So when Bohr said that, can you give a physical way or thought experiment to illustrate why uncertainty principle comes about? Then Heisenberg gave his gamma ray thought experiment. He said that suppose you have an electron and I want to measure its position. What will I do? I have a lens here. I can only see photons through the lens. So I'll take photons, bombard electron with the photon, and when the photon gets scattered out of the electron, I'll collect it over the lens, and from the position where the photon comes, I measure the position of the electron. But then you all know that there is a diffraction limit which says that there is an angular resolution. The resolution of a lens, delta theta, is 1.22 lambda divided by d, where d is the diameter of the lens, lambda is the wavelength of the light that is being used, and delta theta, that is the error in the angular separation between the 2 points. So if you want to measure the position very accurately, the delta theta must be very small. That means lambda must be very, very tiny. But if the lambda is tiny, then the photon has a high frequency, and when it interacts with the electron, it will impart an uncontrollable momentum to the electron. And the photon can be found anywhere within the lens D. And therefore, you don't know how much momentum it has transferred to the electron. So, if you want to increase the position accuracy, that means delta theta to be small, lambda has to be small. But if lambda is small, then the momentum imparted to the original electrons whose momentum was well defined, but after the interaction, the momentum is not well defined. So automatically you have delta x into delta p not being 0. Rather, it is greater than h divided by 4. So this is the gamma ray microscope thought experiment of Heisenberg. But the real theorem that you can prove is because of the fact that the position operator and the momentum operator, they do not commute. And that is the reason why you have momentum uncertainty. And as I said, the uncertainty principle can be used to talk about how virtual particles are created, or for the matter that for a harmonic oscillator, the ground state is really not 0. You might ask, why is it so? After all, if you have a pendulum, then classically, what is the lowest energy of the pendulum? When the pendulum is not oscillating, it is just sitting quiet. Okay? But clearly, this can't be true quantum mechanically. Why? Because the momentum cannot be at rest. Because if it is at rest at a given position, it violates uncertainty principle. It is at a position, and rest being momentum is 0. So therefore, uncertainty principle says that the lowest energy of a harmonic oscillator is not 0, but there is 0 point energy, which is half h bar omega, where omega is square root of k by m, k being the spring constant. So using uncertainty principle, you can estimate what is the ground state energy of an oscillator, or for that matter, you can estimate the ground state energy of any quantum mechanical system using the uncertainty principle. This is what we teach in our first semester quantum mechanics course, how to use uncertainty principle to estimate, may not be fully accurate, but estimate the ground state energy. I hope I have answered your question.
Yes. And sir, how was the value of the Planck's constant discovered or it came up?
Yeah, so initially when Planck derived his formula that explained the observed pattern, the value of h was not used. He said that let h be some constant. But by comparing his theoretical formula to many, many observed Planck spectrum at different temperature, the value of the Planck's constant was determined. In fact, one of our first semester optics lab in our MSc physics course uses the black body spectrum to measure the Planck's constant. Although I am told that this experimental apparatus has a lot of problems and it gives a lot of errors. But today, many experimentalists have figured out very novel and very clever ways of measuring Planck's constant. Photoelectric effect is another way you can measure the Planck's constant.
And um, um, the electrons can be the photons can be detected when when they are unobserved they get a wave state, and when they're observed they get a particle, display the particle nature, but when being unobserved how can you know that it is showing the wave nature or probability thing, that one?
When you're not observing, you don't know anything physical about it. All you know is determined by a quantum state. That is the whole thing, philosophical change that quantum mechanics brought about. That is, you can only talk about the abstract state vector or the wave function of a system if you're not observing. You can't ask what is the momentum, what is the position, what is the energy. You only say that, well, this is described by a complex valued wave function. You don't know where it is. You don't know what energy it has in general, of course, unless it's the energy eigenstate. You also don't know what its momentum is. So you don't know the physical, the values of the physical quantities associated with the state. All you know that it's a mathematical wave function, which is complex in nature. When you measure, you alter the wave function. And that's the whole collapse of the wave function I was talking about. Measurement always brings about a change in the wave function. But the change is probabilistic, and that is a big mistake. I hope I've answered your question, meaning that between two observations, you can't say anything physical about the system. All you can say is that there is the state describing the physical system.
Yes, thank you, sir.
Most welcome.
Thank you, Soumya. Kawaljeet has a question. Would you like me to read or would you like to unmute and speak?
Yes. So, sir, classically, even though electrons do not spin, but they have their angular momentum. So, what's the reason behind this, their angular momentum? Do quantum mechanics explain this, or it is just an assumption?
That's a very good question. Okay. Yeah. So, Kawaljeet has raised a very important point. Yes, electrons have spin angular momentum and they have been measured. I mean, in the Stern-Gerlach experiment and other experiments, we know we have measured the angular momentum spin angular momentum of the electrons. But this spin angular momentum of an electron, you can't think of the electron being like a ball and rotating about its axis, because you can immediately show that if you assume that, then the surface of this ball would be moving with greater than velocity of light, which is not allowed by special relativity. So uh, there are two questions. One is that how do we therefore understand the spin angular momentum? Well, the first answer to this came from Dirac's equation. So Dirac's equation explained why the electron should be spinning. Let me see whether I can get the slide. So it is a Dirac equation. Yeah, here I got it, but then it is Dirac who showed, gave the natural, yeah. So Dirac wanted to get an equation, the so-called Dirac equation, where where the time derivatives and the space derivatives, they were all first order. In the non-relativistic Schrodinger equation, time derivative is first order, while space derivative is second order. Dirac wanted to have a relativistic equation in which time and space have equal footing. And in the Dirac equation, where this del mu is del by del x mu, okay, and there are these, and Dirac, when he did that, he showed that if you want to have a consistent equation where time and space derivatives are both first order derivatives, then psi cannot be a function. Psi has to be a column vector, psi 1, psi 2, psi 3, psi 4. So it is a column vector like this. Yeah. So it's a column vector. And the entries, as you can see, either you can have positive energy solution or negative energy solution. And let's take a positive energy solution. You can have two independent, linearly independent positive energy solution, 1, 0, 0, 0 or 0, 1, 0, 0. Then Dirac asked, what are these different from? And he showed that 1, 0 corresponds to one positive angular momentum, 0, 1 corresponds to negative angular momentum, although the orbital angular momentum is 0. So although orbital angular momentum is 0, but there is an extra angular momentum, and only when you add to the orbital angular momentum, the net angular momentum is conserved, and therefore this extra angular momentum must be the spin angular momentum. So the real reason why electron, quarks, they have a spin angular momentum is because their state is described by a Dirac spinor, meaning it's a 4-component object, psi 1, psi 2, psi 3, psi 4 in a column vector. Okay. So that is how spin got explained. So spin angular momentum doesn't have a space-time representation unlike the orbital angular momentum. Orbital angular momentum, as you know, is r cross p, where r is the position vector, p is the momentum vector. R cross p gives you the orbital angular momentum of a particle. While spin angular momentum cannot be obtained out of r cross p, but it's an intrinsic angular momentum associated with what kind of particles are you talking about. If you are talking about fermions like electrons, quarks, neutrinos, then they follow Dirac equation, and the Dirac spinor that has the spin degree of freedom. While bosons like photons, gravitons, they are vector fields, and the vector fields gives rise to their integral spin nature. I don't know, Kamaljeet, whether I have answered your question.
Yes, sir. Yes, sir. So, sir, it's a mathematical concept which we are calling intrinsic angular momentum.
Yeah, but now we must all realize that at the very fundamental level, the nature is mathematical. Even forget about spin angular momentum, the state of a quantum mechanical system like atom, etc. They are all complex wave function following Schrodinger equation. And Schrodinger equation solution will depend upon the Hamiltonian operator, which is a Hermitian operator. These are all mathematical. So
Yes.
ultimately, at the fundamental level, nature is mathematical. As to why nature is mathematical, that is a very, very deep question. Not uh, uh, no one probably know the exact answer. All I have speculated on it. I can only give my own idea that nature whatever nature is, its language must be logical and uncontroversial, and it should be quantitative because when we make measurements, we only measure numbers. So therefore, if nature adopts a language which is logic and based on numbers and it has no paradoxes, then only language which has this is mathematics. And therefore, mathematics is the language of nature.
Yes, sir. Sir, thank you so much for the answer.
At the fundamental level, the only way to understand the reality of fundamental physical system is to delve into abstract mathematics. That's the only way.
Great, Kawalji, your query is answered, right?
Yes, sir. Thank you so much, sir.
Most welcome.
Thank you, Kawalji. So Sudipto Dixit, I guess had a small question. I guess someone tried to answer your question in the chat. Is your query solved or you still want sir to explain? Sudipto?
Yes, sir. Though it was answered very well by one of my classmates, but I wanted to ask that do quantum mechanical models obey the conservation of energy? And if they don't, so do we have a reason for that?
Well, the if your Hamiltonian, if your quantum mechanical system has a Hamiltonian which doesn't depend upon time, then energy is conserved. But that's also true in classical mechanics. If your classical mechanical system, your potential, the potential energy, if it is time independent, then energy is conserved. But if your potential energy is time dependent, energy is not conserved. So that is also true in quantum mechanics. If your Hamiltonian has a potential energy which is not time dependent, like if you are solving for the hydrogen atom problem, then in hydrogen atom the potential is simply E square by R. It doesn't have time dependence. So your energy levels or the energy eigenvalues are time independent, and you have conservation of energy in the case of hydrogen atoms. Only if the atom interacts with the electromagnetic wave, then the electromagnetic wave, the electric field and magnetic field are changing with time. Therefore, the Hamiltonian will have a electromagnetic term which is time dependent. Then energy is not conserved, and therefore the hydrogen atom electron will be ejected under certain condition when electromagnetic wave interacts with hydrogen atom, and so on.
Yes, sir. Thank you.
Most of it.
Thank you, Sudipto. Now, Shreyas had a few small questions. Shreyas, go ahead if you can unmute and speak.
Yeah,
Otherwise, I can read out your questions.
sure. Good afternoon, sir. I
Good
wanted
afternoon.
to ask about this recent news about quantum entangled tardigrades. So,
What is that? What is that? What is this tardigrade? I don't know about it.
Like these are the small animals of like 1 millimeter length, and I read in the news that they are like quantum entangled, and so I wanted to ask like what is
I
like
I'm very surprised to know it because you see, uh, every living system that I know of at least should have Avogadro number of molecules in it. And a Avogadro number, remember, Avogadro number is 6.023 into 10 to the power 23.
yes, sir.
So this many molecules, in order to be described uh, in the form of quantum wave function, they have to be in a condensate state. And I don't think uh, any living system can be in the form of Bose-Einstein condensate state. So I'm very surprised as to what you are saying.
Hel-
They have been
hello,
present here. You.
hello.
Yeah.
Yeah. Good morning, Patrick. Shukanta this side.
Hi. Yeah.
Just tardigrade was recently is news. Nature in the came out in Nature. They are
Hmm.
doing this experiment. They want to now send it to space as well to see the entanglement. It seems it is not the real entanglement that we understand in quantum mechanics, but some sort of para experiment. I mean, as you are correct, you can't have a system of 6.023 10 to the power 23 atoms and we can do this experiment. But yes, the news is also correct, but it's at the very preliminary stage. Tardigrade at some microorganism probably that is there in the deep sea level. They are trying to do some experiment.
No, but what experiment? I mean, clearly the whatever creature, microscopic creature, they can't be quantum mechanical.
They are not.
Ultimately,
They are not. As
why
you're
a
correctly
living
saying, they are
system
not.
cannot be quantum
They
mechanical?
are not. They are not. So they want to
Because,
see. Yeah.
in fact, I have written an article why a living system should not be quantum mechanical, because a living system has to exhibit determinism. That is, if I give a food particle near the living system must come and eat it, while quantum mechanical systems are probabilistic. So, a living system should not all the time behave in a probabilistic manner. It should, at a given time, it should multiply, it should reproduce. So determinism has to be exhibited by a living system, and therefore living system must be made out of so many quantum systems that on an average it must behave as a deterministic system. So I have expressed these thoughts in an article which was published in one of the magazines of St. Stephen's. And I would be very surprised that you have a quantum mechanical living system, because that will violate the
No,
whole
it's not
definition
quantum
of the living.
mechanical. Probably, yeah, it's not quantum mechanical, as you correctly pointed out. But they are talking about some. It's very disturbing that how they. In fact, there is a lot of hue and cry why they are calling it to be a quantum system. It is not a quantum system at all in that sense.
And I will be again very surprised that if you have a classical system which exhibits entanglement,
Yeah.
because I mean, it would be very interesting to find a classical system which is entangled. The reason why classical systems don't show normally entanglement is because in quantum mechanics, since every system is described by a Hilbert space, if you have 2 degrees of freedom, the net Hilbert space is direct product Hilbert space, and therefore the wave function has to be product of wave function. While in classical mechanics, we know that if you have 2 systems, one with momentum P1, another with momentum P2, the combined system is not P1 into P2, it is P1 plus P2 as a momentum. So therefore, in classical system, you don't, even for classical waves, you don't have entangled classical waves, because 2 different physical waves, if I want to talk about, then it is not the product state of 2 waves, and therefore you can't talk about 2 classical entangled waves. While in quantum mechanics, if I have 2 photons, then Hilbert space of one photon and Hilbert space of the photon, the combined Hilbert space is direct product. You always end up with product states, and superposition of two product states is an entangled state. So therefore, it'll be very surprising that I have a living system which can be in an entangled state with another living system. Well, was I audible?
Yes, sir.
Yeah,
You are audible. Yes, your query was answered.
Yes, sir. Thank you.
Yeah. So the main answer to your question is I have not read about this new news item. So let me go back and see what are these tardigrades and what quantum entangled experiment they are proposing. So my correct
Sir,
answer
this has
to your
also
question is
appeared
I
in
don't know about
archive in the December. There's an archive paper in Quantum PH on this by this
Okay.
experimental group.
Okay.
I've also not read the paper, but
yeah, I'll look into it because it is.
Yeah, I have not read it in detail, only seen the abstract, but this has appeared in archive also in Quantum PH. But whether it is, I mean, whether their claim is true or not, I don't think that has been really verified.
Okay.
But it is not just this animal, but it is some kind of a joint state that they have taken of the animal plus another qubit, and that joint state is what they are untangling, I suppose.
Yes, that is the Schrodinger's cat paradox.
Yeah, so it is not just the animal state. Animal is not what they are. Yeah, it is a combined joint state of this tardigrade and a qubit.
Okay, then of course, yes. If the qubit has, let's say, state 1 and the tardigrade is alive and qubit state 0, tardigrade is dead, then that's an entangled state, but that's a Schrodinger's cat paradox.
So actually in the news article, it is projected in a different way. I think one has to read their original article, because news items, they just, make it more sensationalize the things.
Right.
Great. So Anaga, I'm sorry if I pronounced your name wrong, has raised hand. You can unmute and speak if you want to ask the question.
Yeah, thanks for giving this opportunity. So when it comes to mathematics in quantum mechanics, which is quite well established, but the interpretation of the measurements, that is one thing that has got a lot of debate in the past. And so I just want to know your understanding of interpretations, and majorly in most of the books, Copenhagen interpretation is widely described, whereas recently what I've got to know is many world interpretation is catching a lot of attention. So what's your opinion on that?
Thank you very much for your question. Yes, so Copenhagen interpretation is very old, as old as Niels Bohr himself, where he said that since all measuring devices are large and macroscopic, it should be described classically, and therefore when you make a measurement, there is a collapse, and the collapse should be treated as a rule, and don't ask why collapse is happening. It should be given the so-called Born rule, and you treat measuring devices as classical. But people immediately pointed out that this can't be so. I mean, people like Einstein, people like Heisenberg, people like Schrodinger. Schrodinger gave his Schrodinger's cat paradox exactly to say that Copenhagen interpretation has its lacunae. And many world interpretation is very old. It's 1963 by Everett, and also independently by Bryce DeWitt. And many world interpretation in 1960s itself became very popular, because in many world interpretation, whenever a system interacted with another system, because of the interaction, they became entangled state, and the entanglement never broke. There was no probabilistic collapse. Rather, the entanglement completely persisted. It is just that in many world interpretation, in one world, yeah. So let's go back to this entangled state. So Copenhagen interpretation will say that, well, the two branches, in one which has cat dead and there's a decay, another which cat alive and there is no decay, the two branch cannot exist at the same time. It breaks. The probability half, this will remain, probability half, this will remain. But in many world interpretation, both branches are there. And if an observer comes and opens the box, the observer state will be, he sees cat dead, so observer sees cat dead. And if he sees alive, observer sees cat alive. So the universe itself splits into two branch, where you have observers seeing cat dead and there is a decay, and observers seeing cat alive, cat is alive and there is no decay. And the world itself every time splits. Every time there's an interaction, you produce entangled states like this, and every branch is always surviving. And most, if you talk to most physicists, they actually side with many world interpretation. But there is a problem with many world interpretation. What is the problem? The problem is, how do you get this Born rule? Because Born rule, in this case, because the amplitude is 1 over root 2 for both of the branches, Born will say that this branch will happen with probability half, this branch will happen with probability half. And Born rule has been seen in all experiments, that whenever you measure, you see mod psi square probability. The question is, can many world interpretation produce Born rule correctly? And the point is that no many world interpretation theory has given the Born rule. In fact, some time back, what is his name? The General Relativity, Hartle, and independently Graham or some such, they talked about frequency operator and almost showed that the frequency operator using many world interpretation can get the probability rule. But soon there was a paper by D squares giving a counterexample and disproving that you can get, using many world interpretation, the probability rule. And then there was this entire bandwagon of decoherence people like Zurek's work, etc. They use the decoherence, saying that the environment, since we don't know the degrees of freedom of environment, so you take the many world, but every time the world is branching, the rest of the environment, we don't know the degree, so we must trace over. And when you trace over, yes, you get the Born rule. But the question is, in real world, who does the tracing? Tracing is a mathematical exercise. So why should, after you get the entire entangled state, why should we trace over the environmental degrees of freedom? Who gives the rule that when you don't know the details of the degrees, you should trace over? And why should nature trace over? So these are the questions which have not yet been settled. So some time back, in fact, I have some slides. I had some idea about using general relativity and the fact that time is determined by the local gravity. And when you have superposition, there are two different times, and is a nonlinearity associated with different times, which causes the collapse. But I did not pursue the program because I also could not get the Born rule out of my different time branch and nonlinearity arising. Ultimately, whatever theory you develop, you must reproduce the Born rule of the probabilities. Till then, we don't have a credible theory that will explain why do we see collapse taking place. So to answer the question, The only difficulty in the interpretation of quantum mechanics, everything else is understood. The only thing is, how does collapse takes place? Because after all, the evolution, quantum evolution is given by Schrodinger equation. And in Schrodinger equation, there is no probability entering. So why should measurement, after all, measurement is also an interaction via Hamiltonian. If measurement is also an interaction via Hamiltonian, ultimately Schrodinger equation should tell you what the state is. And Schrodinger equation always tells you an entangled state. It doesn't give you individual branches with probabilities. So this is the only problem that still persists with quantum mechanics. Unless, suppose you say, as the Copenhagen people will say, that Born rule is one rule, it is my postulate. Then, of course, there is no problem. But then you must answer, why is it that the Hamiltonian, which also talks about the interaction between the apparatus and the system, why should that Hamiltonian arising out of the interaction between macroscopic apparatus and quantum mechanics system, why should it not satisfy Schrodinger equation? So the Copenhagen interpretation then has to answer this question.
Okay, yeah, thank you for this answer. And there's one more thing that like puzzles me a lot when it comes to wave particle duality. Like it started with the light first, and then we got to know that even matter follows the same. But classically speaking, light is electromagnetic wave, and particles, the matter has particle nature. But quantum mechanically, they both have this dual nature. But when it comes to mathematics, it puzzles me, how when it comes to matter treating quantum mechanically, we have both first and second quantization approach that I've seen is used. But when it comes to light as a wave, quantum mechanically, matter is like probability waves. It is composed of probability waves which do not have any like physical existence as such. The psi wave function psi, it's a mathematical entity. But whereas in light waves, these are electromagnetic waves which are like these fluctuations in the field. So I have at least not seen any first quantization approach for the light. I've only seen the second quantization approach mathematically. So I just want, it just makes me wonder, like quantum mechanically, why this difference is there, mathematical treatment, and how do we interpret these things?
Good question. First of all, let me tell you that this first quantization and second quantization approach should not have been described by books. There is no first quantization, there is no second quantization. I know old books talks in terms of first quantization and second quantization. Actually, there is no first quantization and second quantization. There is only one quantization. So whether it is light, whether it is particles, everything is described by a quantum field. So for example, in the case of light, light can be described by a field that is a operator, namely the vector potential A mu. In classical electrodynamics, as we know, that you have the vector potential A mu from which you can get electric field as well as a magnetic field. For example, curl of the AIs, the curl of the three space part of the vector field, vector potential will give you magnetic field, and del 1 over C del A by del T, or rather, 1 over C del A by del T minus grad phi will give you the electric field. Okay, so these are classical electrodynamics, but the same vector potential, that is A0, which is the electrostatic potential phi, and the vector potential A vector, they, when you treat them quantum mechanically, they are now operators. And when you say I quantize, what do I mean by saying quantize? That can I get the Hamiltonian for this problem, and can I get all the states which are the eigenstates of the Hamiltonian, and you can do it. I mean, that's what we used to have a course called radiation theory in MSc physics. Now that course is not there, but that course was very useful because it told you that when you put phi and capital and the vector a, the so-called a mu, the four potential, treat them as operators, then electric field and magnetic field themselves become operator, and the classical energy density, which is E square plus B square divided by 8 pi, that becomes now a operator, and you can immediately write down what are the ground state of the operator. The ground state is a zero particle state, and you can have many single particle states, single photon states of any wave vector k, and you have all the particle states. All the eigenstates are known. Now, for the free electrodynamics, you have solved the problem. So the entire free electromagnetic waves, when you say I have quantized it, what you have done is you have just put the vector potential a mu as an operator, written down the energy density E square plus B square by 8 pi as a corresponding operator, and got all its energy eigenvalues, namely the energy values for different photon quanta, and energy states, namely photon state, either single photon, double photon, any entangled photon. All the states are known. These are called the Fock bases. And you know that there is no second quantization. There is only one quantization. Similarly, for electrons, you can do the same thing. You can take the Dirac field. As I said, electron is a spin-half particle, so it is described by the Dirac-Spinor psi. But instead of treating psi, don't treat psi as a wave function. That would be a wrong thing to do. So the older books, they treated psi as a wave function. Then they said, oh, I am quantizing the wave function. These are clearly wrong. You don't quantize wave function. You only quantize operators. So psi should be treated as an operator. Then your Lagrangian for the Dirac field is I gamma mu psi bar del mu psi minus I gamma mu del mu psi bar psi. You can write down the Lagrangian density. You can write down the Hamiltonian density. Once you write down the Hamiltonian density, you use A and B operators, just like for photons, you did A and A dagger operators. This we learned while doing harmonic oscillator itself. And you can get your creation and annihilation operators, and you have done it. And so you're not distinguishing photons and particles. Particles, photons, everything are treated in the same way. So in the canonical quantization program, every entity in the universe is treated in the same way, whether they are neutrinos, whether they are gluons, whether they are photons, whether they are W bosons, everything is treated in the same way. So there is absolutely no ambiguity in the mathematical machineries. Even in the interpretation, there is no ambiguity, because ultimately what you measure is from the quantum postulate. The only thing you measure in your laboratories are the eigenvalues of the different operators. So when I say I've seen the photon, have you seen the photon energy? You say yes. Well, that is one of the eigenvalues of the photon Hamiltonian, which is integral E square plus B square over the entire space, and so on. Have you seen the photon in the space? The answer is, if I've seen the position, yes. You take the field operator, you take the state, ket psi, and sandwich it between the vacuum state and the field operator. That is your probability amplitude of finding the particle in a position. So these are all, there is absolutely no interpretational ambiguity in any of these. I agree that when I was, because after my MSc, I joined particle physics as my research topic in IISc Bangalore, and I was reading quantum field theory. I was reading old books. There was the first quantization. I was getting thoroughly confused. I started with Bjorken first volume, where you had relativistic wave mechanics, then second volume quantum field theory, second quantum. These are all old books. They created enormous problems. But then I realized that these are wrong books to learn quantum field theory. The present set, for example, Weinberg's 3 volumes, they're excellent. They're absolutely axiomatic, logical, no ambiguity.
Okay, thank you for explaining that. But like conceptually, I'm still like struggle to understand the wave particle duality, and uh, you know, like consider comparing it with classical mechanics. I feel that like in quantum mechanics, this dual nature for both matter and light. So I feel that I mean, this is my opinion that like this wave nature when we consider for the matter particles, it's very like kind of abstract to really understand. It's like probability waves, how to
No,
it's
why
very
are you talking about probability waves at all? I mean, the same thing I can say about photons. All I can say is if I take electrons, pass it through 2 slits, I get interference pattern. That's physical, no?
yes.
So what I see in this experiment, whether I use electrons or photons, I see these are concrete, these are experimental findings. My question is, how do I explain when I am doing this with electrons? The only way I can explain is to get interference pattern. Somehow 2 things must be getting added. So it is psi1 plus psi2 getting added, but position is obtained not by psi1 plus psi2, but mod psi1 plus psi2 whole square. And then I explain this interference pattern. So ultimately, let me ask you, even classical mechanics is not all that concrete. When I was learning classical mechanics during my MSc days, when I was introduced Lagrangian, I kept asking, what is the physical significance of Lagrangian? And my teacher could not explain that time what is the physical significance of Lagrangian. But he should have told me that not all things that you introduce in your physics course has to have physical significance. After, like for example, when I was reading electrodynamics, I was treated to vector potential. If I ask what is the physical significance of vector potential, no one can give the answer because you never measure vector potential, because what you measure is magnetic field. Curl of A is the magnetic field. Vector potential can never be measured because anyway it's arbitrary. You can add to it one gauge. So not everything that is in physics are directly related to physical observation, and therefore not everything in physics, like as I said, Lagrangian or quantities associated with canonical transformation in classical mechanics, have physical interpretation. Ultimately, the physics comes when you're trying to explain experimental result. That is where the physics comes in, but that physics necessarily have to use the mathematical formulation, whether it is classical mechanics or whether it's quantum mechanics. Classical mechanics appeared to us more concrete because we live, I mean, our perception, human perception is classical, and many of the results we can imagine pictorially, while pictures have no place in quantum mechanics. That's the only difference.
Okay. I mean, I'm not still completely convinced, but I think I need to go back and read more.
See, the reason why classical mechanics appears to have concrete, because when I throw a ball, I can, without even seeing the ball's trajectory, I can imagine the ball's trajectory. But as I told you, that actually no object has any trajectory. Even the ball's trajectory is only a human construct. If I were not observing at every instant, I don't know whether the ball would have a trajectory. Like, for example, when a high energy particle goes through a scintillation detector or a cloud chamber, there's a trajectory. But if you actually look at it from the point of view of particle physics, it is not really the trajectory of a elementary particle. Far from it. What you see is the traces of where the detectors have got detected. That is where the particle has interacted. It has nothing to do with the particle's trajectory.
Mhm.
So all I want to point out is that it is only the familiarity which makes us feel that something is more concrete and less abstract.
Mhm.
People who are dealing with quantum mechanics, I think for them, they have developed so much of intuition in quantum mechanics. For them, quantum mechanical systems are as concrete as classical systems. It's only the question of familiarity.
Okay. And also this like classical mechanics is deterministic in nature and quantum mechanics is probabilistic nature.
Oh, yes.
So
No, that of course. But as I told you, the probability part uh, is the most mysterious part of quantum mechanics. The Schrodinger equation, which is a fundamental equation that governs the dynamics, that doesn't have any probability. So yes, in fact, I mean, Einstein was known to put his finger uh, into the right spot. I mean, Einstein only right away said that God cannot be malicious. He cannot play dice with nature. So Einstein also realized that this is the key problem with quantum mechanics, how to understand the probabilities. And the fact of the matter is, even today, we don't know where the probabilities are coming in the case of quantum mechanics. Although we know, right, from the semiconductor devices to atomic experiments to LHC, everywhere Born rule has been verified again and again. So Born rule works, no doubt about it. So key question is, starting from Schrodinger equation and Hamiltonian for interaction, can one get Born's rule? That is the only unsolved problem in quantum mechanics.
okay.
Because after all, your Ehrenfest theorem, which connects quantum mechanics to Newtonian classical physics, which takes average, it relies on the Born rule. So if one can explain how Born rule and probabilities emerge from Schrodinger equation, one would have solved everything.
Okay, and this when it comes to applying quantum mechanics to a system, so like is there any kind of a like distinction where depending upon the like how significant the quantum effects are for a system, so it depends on that. So like when it comes to describing a classical system, we don't have we don't use quantum mechanical approach, though we consider that it's more appropriate and it's complete. So what do you have to say about that?
So is your question that for quantum to describe an experiment in quantum physics, you have to necessarily use classical physics? Is that the question you're asking?
What I'm saying is like we know that classical mechanics has got limitations. We can't apply this to any system, whereas quantum mechanics is more complete approach. But then we have limitations in terms of the complexity in calculation. So so where does this distinction hold? Like, you know, how do we?
No, are you talking about the difficulty level? Let me tell you, even in classical mechanics, three-body problem has not been solved exactly, even today. So I don't think complexity is the main issue. There are problems in classical mechanics which has persisted for many, many years and have not been solved. I think there's something more to it. It is this, that there are quantities in quantum mechanics which doesn't have classical counterpart. Like, for example, the spin angular momentum.
Yeah.
The spin angular momentum of elementary particles, there is no classical analog to it. So, therefore, you will say, oh, quantum world is queer. We don't have a image, corresponding image in classical physics. If you are saying that, I agree, that is true, because in the fundamental world, is always something which is beyond us, whether it is the small scale fundamental world of quantum systems or whether it is the large scale fundamental system of the cosmos. They are always beyond us because our senses, human being with whatever senses we operate, we can only understand things that are near to us, which can be directly understood with our senses. But if you have a system like the isospin uh, of elementary particles, the isospin of elementary particles don't have any analog in classical world, and therefore you can't even feel with our senses the isospin quantities.
Mhm.
But that only means that, well, human beings are, we are not the ultimate, we are not the ultimate probe of the ultimate reality. So we have limitations. So therefore, there are many things of nature which we don't have proper senses to perceive them. And it is here I feel that what can provide us the extra senses is abstract mathematics, because abstract mathematics is about structures which have nothing to do with our senses, or which have nothing to do apparently with the world we see. And time and again, the pure mathematicians' work, a part of their work, have come to describe new physics so beautifully, whether it is general relativity, the tensor calculus developed much before general relativity came, or the Hilbert space of David Hilbert developed much before quantum mechanics came. And these are some of the things which I have discussed in some of the articles that I wrote on nature of mathematics, or pedagogical unreasonable pedagogy of mathematical physics. I have expressed all these ideas in two of my articles. Um, and I feel that mathematics is very, very important because human beings have only five senses. We can't go beyond. But through abstract mathematics, we can uh, go beyond our limitations posed by our senses. And that's the reason why fundamental physics necessarily have to be based on highly abstract mathematics.
Okay. Okay.
Okay, so
Yeah, I'm sorry to interrupt. Actually, ma'am, this is going beyond the interest of our students, the discussion. So, can you please let our students ask the questions now?
Yeah, sure. I'm
Yeah,
sorry for taking so
please.
long. Thank you.
No, no, it's all right.
also it's getting pretty late on sir's part as well.
No, no, I'm
Nilanjan has a
fine.
question.
I
Let
One of the things that gives me pleasure is discussing with uh, students.
That is great, sir. So Nilanjan, you can unmute and speak now. You have raised your hand. Okay, since Nilanjan is not unmuting, Khushi Lalit also had a question. Would you like to go ahead and ask?
Yeah, sure. Thanks, Manish.
Yes, ma'am. Yes, sir. Can I speak?
Okay, okay.
Okay, Nilanjan, go ahead.
Sir, my question was that from in the double slit experiment, it is known that when we pass any either electron or photon through both of the slits, if we place some detector, then the wave function get collapsed to one single state. But instead of placing a detector in the double slit, suppose in the screen where the interference pattern occurs, if we place another two slits and block the other interference pattern and take particular two interference pattern, what will happen if we place another screen away from it?
No, no, you said too many things. I did not get the picture of what you're trying to ask. Are you saying that, yeah, there is one thing which is described in many books, that if you try to find out through which slit the electron is going,
Yes, sir.
then you will never get the interference pattern, which is true. Because if you try to put a detector near one slit and try to figure out whether the electron is going through that slit or the other slit, then you can prove using uncertainty principle that you will never see the interference pattern. After that, what do you want to do?
I was saying that I don't want to place the detector in the slit. I just want to observe the pattern, and instead of observing the pattern on a screen, I want to place another two slits and blocking other interference pattern and focusing on two immediate interference pattern, means
Yeah,
bright
so
fringes.
if you put another two slit, these are the kind of work which Tabish Qureshi and his students do in Jamia Millia. So, for example, if you put, so you don't put a detector, you put another screen, opaque screen with two slits. And depending on where two slits are, you can show that if your two slits are positioned where your dark fringe will appear. So, supposing you put your the second opaque screen with two slits, and the two slits are in the position where you should have observed dark fringe, then you will never see any other particle going past. While if you put them on bright fringe, then you will see particles, and again you will see two slit pattern beyond the second opaque screen with two slits.
So then, how can you know that in the first part we did not know that the particle was passing through one slit or the two slits?
No, because you did not detect. So therefore, the wave functions interfered. No, where you have put your second screen with two slits, what is the state? It is psi1 plus psi2 which is coming there. See, originally you had a single electron coming with state psi. When it passed through two slits, it became psi1 plus psi2. Now psi1 plus psi2 is coming and hitting the second screen with two slits. And if your slit is in a position where psi1 plus psi2 is 0, and other slit is also where psi1 plus psi2 is 0, if the wave function is 0, there is no particle. So therefore, on the other side, you will not see anything. So you might ask, oh, then where has the particle gone? Have I lost out on conservation of energy? The particle will hit the opaque part of the board, as simple as that.
Okay, sir.
But good that you are thinking this way, because it is this way of thinking while you are learning quantum mechanics that gives you the intuition about the subject. So that's how to build up your physical intuition about quantum mechanics, to think of all such possibilities.
Okay. So, Nilanjan, your query is answered?
Yes, sir. Thank you.
Great. Khushi, would you like to speak now?
Yeah. Hello, sir.
Hi.
So my question is a little hypothetical. So, if the electron was conscious, then what would it see while going through the double slit experiment? Like, what will be the electron picture of the scene?
Yeah, very good question. Because when I started learning quantum mechanics, I had asked myself the same question. Yeah. So the first thing is to ask, what is consciousness? Okay. So as I told you, as I had given one answer to a previous question about something called tardidet or some such thing, my personal belief is consciousness is a collective activities of many cells, namely the neuron cells in a brain. Okay. And living systems or consciousness is a function of many, many, many molecules, at least an Avogadro number of molecules. Okay. So whether it is life or whether it is consciousness, it is a feature exhibited by a system having more than Avogadro number of particles. And therefore, according to me, a single atom or two atoms or three electrons cannot constitute life or consciousness. And therefore, a question like what will an electron think is a question like if I were traveling with speed greater than c. The question is of that category. I hope I have answered your question.
So the last point I did not understand, like traveling with C.
See, very often when one is learning relativity, sometimes you bring paradoxes. Say, I have disproved physics because if I am traveling faster than c, I will prove relativity wrong. The answer is obviously you will prove relativity wrong because relativity's fundamental tenet is the two postulates from which you can prove that nothing can move faster than the speed of light. Because special relativity tells you that if you have a particle with rest mass m0 and if it moves with velocity v, then the measured mass will be m0 divided by square root of 1 minus v square by c square. So v cannot be greater than c, because if v becomes greater than c, then the inertial mass will become imaginary, and mass cannot become imaginary. So therefore, special relativity tells you that nothing can move faster than speed of light. So therefore, if you raise a question that how will the world look like if I move faster than the speed of c, is exactly like your question, what will the electron see when it is passing through slits? Because that's what my answer is. The electron or a single atom or two atoms, three atoms cannot have consciousness. Just like a particle cannot move faster than the speed of light, my thesis, this is of course my conjecture, that no living system or living activities can be obtained using 3 or 4 atoms. So, to answer your question, an electron, according to me, cannot have consciousness.
Yes, I got your point. Thank you so much, sir, for answering. And so one more thing. Sure. Why the de Broglie proposed the de Broglie wavelength and not something related to a de Broglie frequency, or is frequency even defined for matter waves?
No, of course you can also define frequency, because ultimately E equal h nu is also a fundamental result that you can do when you do a quantum field theory of elementary particles. You will see that for elementary particle, the quantum E is equal to h nu is still valid. But E equal to h nu was given by Planck. Okay. So therefore de Broglie gave something new. He gave you a result which said momentum is h by lambda, which was a new result, right? I hope I have answered your question.
Yes, sir.
So
yes,
in
sir.
quantum mechanics, if anything has a definite energy E, then its frequency will be E divided by h.
Khushi, is your query answered? Any other doubt?
It's answered. And so one last thing. So the slides that you showed, the handwritten one. So the cats were there. So were they drawn by you?
That's right. Yes. The pictures that I showed, sketches, they were all drawn by me.
Okay, sir. Very nice drawing that was. Thank you.
Thank you.
Excuse me, sir.
Can I add something on the lighter vein here? Since Khushi has brought up this thing about the cat, that your wave function says with the talk the cat is dead. I think we are all alive with your talk, not dead.
Oh, that is only because cobalt nucleus has not decayed.
Yes, obviously. Thank you.
Excuse me, sir. I would like to add something to Khushi's question.
Yeah.
Yes, so relativity we know as a definite fact is correct, but consciousness is something that we don't know yet. So what if consciousness is something more fundamental, and what if electrons do have it?
No, but it depends upon how we define consciousness. According to me, consciousness is all the activities of brain in our awakened state, right? Or do you have any other definition of consciousness? To me, consciousness is all activities of my brain in my awakened state is what I call conscious state, consciousness. And therefore it is the activity of a brain. And brain is made out of billions of neurons and all the electrical impulses, all the chemical reactions, glucose being used to generate energy by the mitochondria inside the neurons, and so on. All those are the physical basis that are taking place, and the activity is what we we call as consciousness.
Yes, so that can be one definition of consciousness, like consciousness as an emergent phenomena. But like different physicists have different theories on consciousness. We don't know yet for sure what is exactly the nature of consciousness. Like it can be something more fundamental, like a field or something.
No, that people like Maharshi Mahesh Yogi, Steam
So
used
those
to
are
talk
like
about the
those are the
unified theories of
pseudoscientific
consciousness
claims.
and so on, using big words. But see,
those are the pseudoscientific claims. I'm not talking about those. Like,
no, but
what if
unfortunately, it is like this. In science, normally the principle that is adopted is what I can measure and how do we explain the measurement. So the whole neuroscience division, when they deal with consciousness, they will conduct experiment. They will say that what they will do is they will show a particular person whose brain activities are being monitored, show some pictures, and they will try to figure out which part of the brain activity is going up. And that's how they are constructing theories about consciousness.
So I think we are already running past time. So let's take one last question from Suhas. Suhas, you had a question?
Yeah.
And then we can end the Q&A session.
Good afternoon, sir. My question is that when you explained about superconductivity, you told the Cooper pairs are creating the distortion. The first part of my question is:
No,
is
not
this
Cooper pairs are not constructed distortion.
the electrons?
I tried to explain physically. This is not my explanation. This is a wonderful article written by Weisskopf on the physics of Cooper pair formation that I had read long time back, when probably in 1981. And I really liked Weisskopf's explanation as to why Cooper pair forms at all when two electrons should be repelling each other. And his sort of thing is what I showed as a picture, and that is, I don't know where the slides went. Yeah, so anyway, it will take time. Let me explain. So the way Weisskopf explained the formation of Cooper pair is that first, superconductivity takes place in a crystal. And Cooper, the BCS theory, they explained formation of Cooper pair by saying that two electrons, they exchange phonons and form a pair. What are phonons? Phonons are quantas of lattice vibration. And Weisskopf gave a much more physical feel to explain how a phonon exchange binds two electron. And his explanation is that take one electron, and as it is going by, electron is negative, so it will attract the positive ions. So positive ions collect towards the first electron. Another electron which is coming from far, it suddenly sees that lot of positive ions have got concentrated here. So here, the positive charge density is increased compared to positive charge density there. So therefore, the electron gets attracted to this part. So indirectly, the electron is getting attracted to this electron. And that's how two electrons form a bound state, which is a Cooper pair. Have I answered your question?
Yes, sir, partially. I just wanted to know if these distortions are temporary, right? Like after some time it
Oh yeah,
comes
yeah.
back.
These are time-dependent distortion because uh, but that's a very important point. So unlike most bound state, where in a bound state normally the system is compact, they occupy a small region. Cooper pairs are not like that. In fact, the two electrons in a Cooper pair, they are not correlated in the physical three-dimensional space. They are correlated in the momentum space. So they are actually very far apart physically, just like in this picture. So Cooper pairs are very different from the standard bound state, like an atom. In atom, the electron is very close to the nucleus, right? Not in the case of Cooper pair. In other words, the Cooper pair wave function in three-dimensional position space is very wide.
Okay, so your query is answered, right?
Yeah. Thank you, sir. Thanks.
Okay, so
So
I
one
think
thing,
we have talks on such topics can run for hours and hours long, but since we have limited our time, I think we should end the Q&A section here.
so one last thing, can I say?
Sure, Samir, go ahead.
When we're not observing something, then it is getting probabilistic, right? So
No. When we are not observing, so that is the thing. So you have made some observation first. From that observation, you know the system as a particular state. When you're not observing, then that state is evolving according to the Schrodinger equation. You know nothing else about it. You know, when you did first observation, you had a state and it is evolving according to the Schrodinger equation. So when you're not observing, your state is that state. That is the solution of the Schrodinger equation. Next time when you make a measurement, depending upon what you measured, your wave function collapses to one of the eigenstates. Okay, let me give you a concrete example because these are abstract ways of talking about. So if I have a jar of hydrogen gas at room temperature, then I know at room temperature all hydrogen gas atoms are in the ground state. So therefore I know that the atoms are given by the ground state wave function proportional to e raised to power minus r square by 2a naught, where a naught is the Bohr radius. So that's my initial wave function. Then someone says, okay, and it's a stationary state because its time dependence is only e raised to power minus r by 2a naught into e raised to power minus I e1 t divided by h bar, where e1 is the ground state energy. So the time dependence is trivial. It's only in the phase. But now someone says that, okay, what I do is I shine it with a laser lamp. Then what will happen? The laser lamp, as you know, the laser light is also a quantum light. Its state is also known and the electric field are known. Then what I'll have to do is I'll have to take the laser light state, take the atom, write down the Schrodinger equation and do the evolution. The evolution will give a complicated state. It will really give a very, very complicated state. Now you say, I have a detector. What is going to happen? Sometimes you will see that the laser lamp will tear away one electron from the hydrogen atom. Sometimes they'll do it for two hydrogen atoms. And TFR atomic group in TFR, they constantly do these experiments. And they see various possibilities. Each possibility follows the probability given by the bond.
Okay. So let's conclude the session for now. Okay, so anything else, sir? Okay.
Thank you, sir.
Oh, sir.
Any of the teachers would like to say anything? Kwanta sir, you have unmuted your mic. Would you like to say something?
Yeah. I thank Professor Patrick Dasgupta for this excellent lecture and the long hours. I think It's very interesting, and if I would welcome our students, even if you have question, you can put the questions the mailbox, or he can reach him. Because we know him as a teacher, we know him as a colleague, we know him. He's an excellent. I mean, he comes down to the level. So I request all my first year students who I'm teaching this, I'm addressing to my first year students right now. So please do. You have not asked questions. I understand it's not so easy, but try to for read books, whatever he has suggested. Read articles, and please, if you have questions, you can discuss over mails. May not be you have to always speak out here. I mean, it's not all. I understand it's not so easy to ask question, and you might be having a lot of questions in your minds. So some of the questions can be also discussed with your own teachers when you whosoever is teaching you whatever subject, to all our students, and we can clarify some of the things. Especially I would like to do some question regarding Planck constant, where you said that how it will be determined. Somebody asked this. Patrick sir has already said that we do an experiment in the MSc lab. I would like to that we have in third year in both BSc General as well as I think honors, both the determination of Planck constant, and from there, although we don't do it from the same experiment, same kind of experiment, but by the dimensional argument of the constants involved in diode, also you can explain why that quantity should be of that order. Even without doing that experiment, you can guess why the answer should be that of that order. So one comment is that. And thank you, Professor Patrick Dasgupta, for the excellent lecture and the motivation to our students.
Most welcome. Most welcome, Sukant. Thanks for your words.
Thank you.
And many of the fundamental aspects of quantum mechanics that I tried to convey, it is there in one of my published article of NASI volume, but you can get it from the archive also. You just have to type in the Google 3 phases of Arnold-Bohm phase. So many of the fundamental aspects I have discussed in this article. If you just type in the Google 3 phases of Arnold-Bohm phase, you can access that article from archive.
Great. So concluding today's session, we would like to thank Professor Patrick Dasgupta for being with us here today and introducing us to the mysterious world of quantum mechanics, despite being in a different time zone and staying for so late. Thank you so much, sir. We hope to see you again in the near future, and you definitely sparked the interest of a lot of students in quantum mechanics, giving a new meaning to the name of our society.
Thank you. Thank you.
We also...
Patrick, sir,
yes,
I would also like to thank you on behalf of the physics department for actually giving such a, I will say a beautiful lecture, because this time I also have taken up the topic of modern physics for the first time, and I was finding it difficult how to introduce the failure of classical mechanics and the introduction to quantum mechanics, which I have know now how to do it. And I have even taken screenshots of your slides. I hope you will not mind.
No, not at all, not at all.
Yeah, and sir, I also thank my students who have actually made an effort to revive the society and organize such an event. And I'm also thankful to my teachers for being patiently actually handling this. And I'm also really sorry because Sushil, who had actually arranged all this, he is not well. So he couldn't attend it, and he's in the hospital. So I would like to thank on his behalf also.
I hope it's not Omicron
it's
related.
COVID. Yes, yes, sir.
Oh, I wish him all the best.
Yeah, so I would like to thank on behalf of Sushil also, and I would also like to thank Savinda, because she has also been a very, you can say, a real support to the students and to me for reviving this. And again,
Professor Savinda Kaur herself, her expertise is in quantum atomic systems. So
Yes, sir. And your paper, which you've said, I've posted that archive for the students. They can kind of download it from there. Yes.
Thank you,
Yeah.
Professor Sandra.
So,
Thank you.
thank you by all my heart, sir, for giving
Most
such
welcome.
an
It
encouraging
was
lecture.
fantastic interacting with you all.
Thank you.
Take care.
Great, sir.
Take care,
Have a very
everyone.
good night, sir. Night sleep.
Yeah.
Thank you. Thank you.
Good
Take care.
night, sir.
Okay.
Yeah.
Just a few last
Thank
words.
you, Patrick. Remo from this
Most
side.
welcome.
Thank you so much.
Hi, hi,
Wonderful
hi,
talk.
Ramo. Yeah. Take care.
Just a few last words. If anyone has any suggestions, then we are releasing a feedback form, and the link for the feedback form is will be posted in the chat box now. And for the future events and for future updates, keep connected with us on social media. The social media links will also be posted in the chat box now. Now, I request everyone who can to turn on their camera so that we can take a screenshot to capture this beautiful memory. Sir, you can now stop the screen share and turn on your camera if it's working now.
No, as I said, even if I turn on my camera, nothing is happening.
Yeah. Okay.
So there's some problem with the system that my video is not working. You can see that although I've turned my video on, but it shows a camera with a slash.
Okay, okay. That's fine. Anyone who can please turn on their camera.
Sir, to access the permission, can you please click on that lock? If you click on that lock sign, that meet.google there, you can find some option regarding accessing the camera. If you give the access.
But this is a problem I've noticed in the past. And what did you say I should do?
Near that meet.google, that hypertext that given the up, yes, that lock sign, lock sign.
Okay.
If you click on, okay,
I think there's a hardware key for the camera to turn off your
the camera, as you can see, is on, right?
Yes.
Camera is on the beat, but there's sometimes on some laptops there's a hardware key to block your camera. Anyway, anyone who can please just turn on your camera so that we can capture this moment. Digvijay, you can. Thank you. Digvijay, let me know if when you're taking the screenshot. Done?
Yeah, just once more on the go for 1, 2, 3, go. Done. Thank you, everyone.
Thank you, everyone. Thank you so much for joining us today. It was a wonderful session, sir. Thank you so much.
Take care, everyone. Okay, be safe. Bye.
Thank you. Thank you, everyone.
Thank you, sir. Thank you.